So last time we hinted at the idea that there could be a relationship between linear maps on one hand, and I'm going to put this in air quotes here, matrices on the other hand. And I kind of left this to you guys to check because we haven't talked about what isomorphism really means for vector spaces yet. But there's another structure which we haven't talked about because linear maps, matrices, they do not merely have a vector space structure. There's another component. And I think we know this, at least intuitively, because since they are functions, if I have two such functions, I can compose them. And since, right, they're linear, they will have the properties of linearity will be preserved when I compose them. And that means that I need to understand then, in this picture of how these things are the same, what does it mean to combine two linear maps regarded as matrices? And towards that end, some of us have probably seen the definition of matrix multiplication, but that's what we're going to be dealing with today. Is I'm going to give you a definition / proposition, which is that composing abstract linear maps, and I'm going to write equals, again, in the same sense as up above, matrix multiplication. And I call this a definition / proposition because I don't know how many of you have seen matrix multiplication before. And so if you have seen it before, then this is a proposition because I'm going to tell you that that algorithm that you learned maps onto, under this notion of is the same as, composition of linear maps. But if you haven't seen this before, it's the first time that you're seeing this concept, then it's kind of just the definition of matrix multiplication. And what I'm doing is not so much giving a proof as much as explaining to you why you might come up with this idea, how you should think about this. So in order to go about the explanation / proof of this definition or proposition, we're going to continue with the theme of what we did last time. So we're going to introduce some notation. So first, let's say we have three vector spaces as above, v, w, and x. We'll take as a basis for the space v. How about v1 through vn? And then for w, we'll take w1 through wm. And then for x, we'll take x1 through x, p. Right, we don't usually use O, so that seems fine. Now we take a linear map T from V to W and a map S from W to X. And we want to look at ST, the composition, and say what happens when I feed in a V. I don't know, how about we call this VK? Excuse me, doesn't matter which one. So what we did last time is we said, okay, when you apply T to VK, since the W's are a basis, we said that you will get out some constants and some combination. We could call this RK. A lot of letters are already in use, so we're kind of hurting for new letters. But we'll call this ARK, and then it maps into the WRs. And then this sum runs over the values of the R's from 1 up to M. Let me just make sure my indexing is correct. We said that the image of VK is the kth column of the matrix of T. This entry is the column, it's the row that varies. So yep, this is right. So this expresses the idea that T of VK is some linear combination of the W's. Well, now I can distribute S, right? S is linear, so it commutes with sums and also with scalar multiplication. And that lets me write S, sum from R equals 1 to M of ARK S of WR. And then we have to know what happens with WR. And we can do something very similar here. Since the WRs are a basis for W and it's mapping into the X's, then I can say that the result is some kind of, I'll use the letters B this time because I guess we already used those. I can say that the result is a linear combination of the x's, where again, since this is the rth guy, the rth basis vector, then it will be, sorry, it should be a sum in here. And I don't know, we already used R. What letters have we not used? Do we use J yet? We have K. Yeah, we can use J, I guess. And go J equals 1 to P of B J R, because it's are feeding the R in, so it's the rth column, XJ. Okay, and now we can sort of clean this up a little bit. I understand this is kind of getting messy, but we're almost done. This is the sum R equals 1 to M, and I'm going to distribute these ARKs inside. J equals 1 to P. How about we put the B's first, right? Because S was written on the left here, so how about we make them match? BJR ARK XJ. Okay, so this is the result of our calculation. What does this mean? How do I interpret this? Well, first off, like we said, this is what you get when you feed in the kth vector. So that means this mess, right, this sum in particular, is what you would find for each of the entries in the kth column. And in particular, the entry in row J, column K, right, for a fixed specific J, would therefore have to be the sum BJR ARK, sum R equals 1 to M. So in other words, if I want to know what is the JK entry, sorry, let me just try to write this from the beginning. This is M of ST, and then I want the J comma K entry. We get this sum out. And so this is a little bit hideous, but if we go and actually work out an example or two of how this works, we'll see that it's not so crazy to interpret what this means. So let's take a look at that. So how about we take the following example from Axler? We have this matrix and this matrix. And we want to multiply these matrices. So this one is a 2 by 4 matrix. This one is a 3 by 2 matrix. And we see here, I always call this the happy face when I'm teaching, because when the twos match up, the inside numbers, there are as many columns as this guy has rows. This ensures that this formula will even make sense. It wouldn't make sense in the first place. Or said more precisely, it shows that the dimensions of the domain and the codomain match up. This thing, in order to use the matrix multiplication formula, probably this isn't super clear, but it will be momentarily, wants to eat in something of size 4, right? This 4 here tells you what the input should be. So the initial input is F4, and what I get out, it takes values in F2. And then this thing goes over to F3. And so as a result, we expect something F4 to F3, or a 3 by 4 matrix. And how does this actually work? Well, to find the JK entry, let's take a look at, for example, the 1-1 entry. The 1-1 entry then has B1R AR1. So in other words, the B's, that's these guys, this entry becomes locked to a 1, and that's the rows. So in other words, to get the 1-1 entry, I'm looking at row 1. Whereas over here for the A's, it's the first column. And then what this says to do is take 1R, R1, multiply them, and then go 1, 2, 2, 1, multiply them, and add them up. In other words, it's saying do the row times the column. And so this is 6, right? First entry times first entry, and 2 and 2, second entry and second entry makes 10. And then in this way, we keep working our way through. For the 1, 2 entry, I have to do first row times second column. You can see why it's important that these things have to match up in terms of the number of columns here, same as the number of rows here. So everything actually does pair. We have 5 and 2 makes 7. And then we continue to 4 and 0, and we get 4. And then lastly, we go over here, 3 and minus 1. I get 3, and 2 times minus 1 is minus 2, so that's 1. And that calculates the first row. Then, to get the next row, we go over here. And I'm saying now I want the 2, 1 entry is second row times first column. And we just continue on in this way. 6 times 3 is 18. 4 times 2 is 8, so this is 26. And I'm going to try to keep this in a thought bubble so we can, I guess, don't have to listen to me do mental math. And now lastly, in the third row, 30 and 12, 31, this one's 20, 15 minus 6 is 9. Okay, so we did it. And that agrees with what's in Axler. So a couple of things I want to say about this. First things first, matrix multiplication is in general not commutative. I mean, partly we can see that because if I switch them, it may not even be defined. For example, if I switch 2 by 4 and 3 by 2, then there's no happy face in the middle anymore, so it's not even defined. But even when they are defined, matrix multiplication doesn't have to be commutative. So in this sense, we're remembering our group theory. I'm just going to write usually not commutative. There are special situations where certain matrices can commute with certain other matrices, which we may learn about later on if time permits. Okay, what else did I want to say about this? Oh yeah, I wanted to show another way of like writing these things down, which can sometimes be helpful. If you haven't seen this before, probably you're scratching your head a little bit trying to verify this calculation and maybe even repeat this yourself. Let me show another way of writing this down that I think helps. It's shown to me by a friend of mine, and so I'm kind of indebted to him for this very clever way of writing things. Let's do a simpler example. Here's just a 2 by 2. Instead of doing rows by columns this way, which is what you should do, it's what the definition is, we take the second matrix and we write it up above. I'm going to erase this now. And the reason for this is because now to multiply this by this and get an answer, you will notice that the rows and columns line up perfectly. So the first row and first column meet right there. And I find that to be super helpful to figure out. Like the thing in the 1, 1 entry is this row and this column. So I get 6 and 12 is 18. Then for this entry, we have first row, second column. 2 and minus 3 is minus 1. Minus 3 and 0, and minus 1 and 0. So that's the answer. Call this example 2 if you want to. I find this to be a much more helpful way of writing things down. I understand that on your homework, it's not going to be that easy to like type this up. Of course, if you're giving me a handwritten solution, you can handwrite it that way. And as long as you indicate kind of what's going on here, maybe you draw me an arrow or you put the times up here or something, I'll know what's kind of going on. Completely fine by me. Okay, and so in light of all of this, this is a explanation / proof of the fact that M of ST is equal to MS MT. where here we mean composition, and here we mean multiplication of linear maps. Sorry, multiplication of matrices, linear maps. They're interchangeable in my head. What can I say? Those of you guys who like giving names to things, when you have a vector space where you're also allowed to multiply, we call that an algebra. An algebra. And so we're talking about how this thing M kind of defines a linear map. It defines an algebra map even. And so maybe now if you like that terminology, you like abstract math, now you have a name that you can put to things. All right. Throughout Axler and the rest of this chapter, there are a whole bunch of nice propositions for how you might practice speeding up your calculations. I don't feel particularly inclined to show these to you because, well, what can I say? It's kind of more matrix multiplication practice. And I don't really think that there's any way that I can help you with that better than just encouraging you guys to take a look at it and work on it yourself. If you know this already, then it's fine, and now your life is enriched a little bit. But if you haven't seen this before, it's not going to click unless you still just start doing some calculations and looking at those propositions. So he gives some half a dozen other examples or so in the remainder of section 3C. I'm going to invite you guys to just check that out and just drop me an email or something if you're stuck. And, we'll get you unstuck and life will be good. But I think that after you've done a few of them, you'll be pretty happy with this. Let's see. Anything other closing thoughts? One of the things that it remains to do still is now that we know about linear maps and matrices, I still owe you an explanation of the Gauss-Jordan procedure and the so-called elementary matrices that sort of make it work. And so this is on the to-do list, but first we have to talk about isomorphism. And so that'll be for next time. Like linear maps, which are isomorphisms. And then we'll talk, and because isomorphism means invertible, we'll talk about invertible matrices as well. And I think after that, you will have everything you need for me to explain to you kind of why these calculations work. Because at this point, we now understand that abstract linear maps can be represented as matrices. We just need to see sort of how this particular process unfolds. All right, friends. So I think we'll stop here, and I will see you guys in the next one. Take care.